Viewers, this is U.A.C.E taking you through A-level inorganic chemistry. So in this video, we are going to be looking at specifically aluminium. So this video has been compiled and revised by U.A.C.E, and you are advised to subscribe to the channel or share it to your friends so that you can benefit as a family. To look at aluminium, aluminium has two ores. So basically in this video we only looked at one. So we have bauxite and we have cryolite. So if you are examined or prompted to state the ores other than bauxite from which aluminium is extracted, or state cryolite. So we are going to be looking at step-by-step extraction of aluminium, and you have to pay attention and you take note of each and everything that was given in this video. Now for those of you who have the notes, you must get a summary book so that you can try to summarize out some factors that you may find important. So you are looking at extraction of aluminium, and we are saying that aluminium is commonly extracted from its ore. And in this video, for the case of this video and for the case of your examination, you will be looking at mainly extraction using bauxite. And alternatively, we have said that the other ore from which aluminium can be extracted is trisodium aluminium hexafluoride, or what you can call cryolite. And we are saying that the impurities that are present in this ore, the bauxite, first of all, we are going to have silica. Now you are going to find that silica is a common impurity in most of the ores that we have in inorganic chemistry. So always don't forget it. Silica is the impurity that is present in bauxite, or it can also be known as silicon 4 oxide or silicon dioxide. And the other impurity, we have iron 3 oxide, denoted by this letter, by this formula. Now there is also there's a confusion. When we usually heat iron 2 oxide that is present in the ore to iron 3, but what is the impurity? Is it the iron 2 oxide or the iron 3? So you find that both of them are present, and when you're extracting, we heat the unconverted iron 2 oxide to iron 3 oxide. For those of you who have been getting confused, so the most appropriate one is iron 3 oxide. So iron 3 oxide and silica or silicon 4 oxide are the major impurities in the bauxite that we use to extract aluminium. So we are saying that the extraction process is divided into two stages, as we are going to see on our next page. We are saying that the first stage is going to be purification of the impure bauxite, and we are saying that purification of the impure bauxite is going to involve purifying the impure bauxite to form pure aluminium oxide. Now you saw the formula of bauxite. Bauxite is aluminium 3 oxide or aluminium oxide attached to two water molecules. So this is the formula of bauxite. Now what do we do in this purification step? Remember, when you are dealing with extraction, everything has to be step by step. So you are saying that Roman number 1, you're saying that the ore is first roasted. Now you have seen that bauxite is having a component of water. So we first roast it using a low temperature so that we can convert. First of all, like I stated in the previous slide, we convert the unconverted iron oxide to iron 3 oxide. However, a student who has said that iron oxide is present as an impurity is also correct, because initially, most of the things present is iron 2 oxide. But also the aim of roasting this ore is to eliminate the water that is attached to our ore. So we are saying that the roasted product is then crushed to powder to form is crushed to powder so as it can form flour, and that flour we are going to dissolve it in concentrated solution of sodium hydroxide. So the equation here you can add the ore is roasted at a low temperature. You can put here an inverted V. First of all, to eliminate the water that is present in the ore, and nextly is to convert some of the antioxide present to iron 3 oxide. Now, what's the purpose of this second sentence of the paragraph? The roasted ore is crushed into powder and then dissolved in concentrated sodium hydroxide. Now you realize that what we are having, dissolution in concentrated sodium hydroxide, is simply meaning that the components that are either amphoteric or acidic are the ones to dissolve, whereas those ones that are basic, they won't dissolve. So if you are to look at iron 3 oxide and you compare it with aluminium oxide is amphoteric and iron 3 oxide is basic. So that means that iron 3 oxide will remain undissolved, and we shall filtrate and we eliminate it. So that's how we can remove iron 3 oxide as an impurity in our ore. So if you go to the second paragraph, we are saying that the dissolution in the concentrated sodium hydroxide is to separate iron 3 oxide from the ore. And the reason for that is because concentrated sodium hydroxide is basic, whereas iron 3 oxide is also basic. So that means that they cannot react. So iron 3 oxide will remain unreacted. But aluminium, being amphoteric, reacts with the concentrated sodium hydroxide solution to form a complex that is soluble. That means that on filtration, we can get rid of the iron 3 oxide and we remain with our ore. So we are saying that being an amphoteric oxide, aluminium oxide and the acidic oxide, remember that we had two impurities, iron 3 oxide and silicon 4 oxide. So we have eliminated iron 3 by dissolving. So aluminium and the other impurity, which is silicon 4 oxide, because it is acidic, they all dissolve in the concentrated solution of sodium hydroxide. And the equations for dissolving are these. So there is a negative here above the O. So 1 mole of aluminium in solid reacts with 2 moles of hydroxyl ions from sodium hydroxide and 3 moles of water to form a complex. And this complex is soluble. Also silicon 4 oxide, which is acidic, reacts with 2 moles of concentrated sodium hydroxide to form a complex, which is sodium silicate, and also water as a byproduct. So we are saying that the iron 3 oxide being basic, iron 3 oxide being basic, and this is important, you have to understand why iron 3 oxide didn't dissolve. Iron 3 oxide being basic does not dissolve, and hence is eliminated off by filtration. And going on to the next thing, we are saying that aluminium hydroxide is then obtained from sodium aluminate solution. Now we obtain aluminium hydroxide in 2 ways. Either you can do it seeding, or you can just pass a current of carbon dioxide gas. So in this case, we are saying that Roman number 1 is going to be by seeding, in which we are going to add a little prepared aluminium hydroxide to our complex or to our sodium aluminate solution so that we can precipitate more of the aluminium hydroxide, a process that is referred to as seeding. But I don't advise this method. I advise you to master the one that is for carbon dioxide, as we are going to be looking at it in the next slide. So on seeding, you have to add aluminium hydroxide already onto our complex, into the solution containing this complex, and as a result we shall form aluminium hydroxide. Here we shall be forming more of it, so you have to pay attention to that. And then to balance our equation, we add hydroxyl ion so that our charges remain balanced. So the other way of precipitating carbon dioxide, which is the most acceptable and which I advise you to go with, is bubbling our solution containing the complex of sodium aluminate using carbon dioxide gas. And we are saying that carbon dioxide, when carbon dioxide reacts with the sodium aluminate solution, we form 2 moles of aluminium hydroxide plus a carbonate ions that remain in the solution. So we are saying that the aluminium hydroxide from either of the methods that we have used above is filtered off and washed and dried. The dry aluminium hydroxide is then heated to form aluminium trioxide. Now this is what we call the purification process. Now remember, our ore is in terms of aluminium oxide attached to water. So why do we go through all this? We go through all that so that we can purify it. We get rid of the impurities. That is Roman number 1, first get rid of iron 3 oxide, which is basic. So to eliminate it, we dissolve it into another basic solution, which we use concentrated sodium hydroxide. And the other ore is silicon 4 oxide. To get rid of it, we seed or we pass a current of carbon dioxide through our solution containing the complex of aluminium, so that aluminium hydroxide can precipitate out. Now after precipitating out aluminium hydroxide, we filter off our solution, and on filtration, we heat the solid that you have got as the filtrate, which in this case is the aluminium hydroxide. On heating it, it will give us pure aluminium trioxide, and that's what we call purification stage. So we usually give this, when it's examined, we give it 6.5 marks or and above, depending on the examiner's interest. So number 2, we are saying that electrolysis of pure aluminium oxide, and we are saying that the pure oxide is first dissolved. It's first dissolved in molten chloride. Why are we dissolving it in molten chloride? We are doing so as to lower its melting point. And we are saying that the molten aluminium oxide is then electrolyzed at a temperature between 800 to 900 degrees Celsius between graphite electrodes. However, you can ignore all this and just tell us that the molten aluminium oxide, now this is very important, everything to be electrolyzed must be molten. Some students make a mistake here and they just tell us aluminium oxide is electrolyzed. We have to say this word because anything to be under electrolysis, it has to be in a liquid state. So you have to use the word molten. We dissolve it in molten chloride so that it can dissolve in it and everything becomes molten. So the molten chloride or the molten aluminium oxide is then electrolyzed. You can say that it's then electrolyzed between graphite electrodes so that you can shorten your work. And we're saying that at the cathode, aluminium will be discharged. And once aluminium is discharged, it's going to give us molten aluminium, which is going to be tapped off at the bottom. Whereas at the anode, since we had one cation and one anion, as you know with issues of molten compounds, let me hope you are good at your electrochemistry. At the anode always we discharge anions. At the cathode we always discharge cations. So at the anode we discharge the oxide ion, and we observe bubbles of a colorless gas, which is oxygen. So to balance the charges, you have to put electrons on either sides. Now let's look at some of the reactions of aluminium. We are saying that aluminium reacts slowly with steam to form an oxide and hydrogen gas. And we are saying that 2 moles of aluminium in its solid state react with 3 moles of water in gaseous state. That means that we need heating. So this is steam. Aluminium, when heated, reacts slowly with steam. So I missed a major important factor here. So you say that heated aluminium or aluminium when heated reacts slowly with steam to form its oxide, which is aluminium 3 oxide, and also hydrogen gas. So part B, when you look at this reaction with chlorine, chlorine is a very reactive gas. So you're saying that aluminium when heated, this is very important when you're stating your statements. We always want to see those conditions. Without heating, that equation is wrong, or that statement does not validate your equation. So you're saying that aluminium, when heated, reacts with dry chlorine gas to form a chloride, which sublimes in air because the chloride is predominantly convalent. Now, the chloride being predominantly convalent, that is as a result of polarization. When you are covering the topic of polarization in physical chemistry, you are told that cations with higher charges and smaller ionic radius have a greater polarizing power. So you find that the aluminium ion greatly polarizes the chloride ion, and the whole compound becomes predominantly covalent or less ionic. So you find that aluminium chloride dimerizes in air. So we're having a simple explanation here. Explanation: aluminium forms a smaller cation with high charge density and high polarizing power. Now whenever you see these are key elements when we are marking your work. Smaller cation is a smaller cation, that means that we are talking about ionic radius. Someone else can say smaller ionic radius with a higher charge density and higher polarizing power. And we are saying hence it distorts. Hence it distorts the electron cloud of the surrounding anions. And we are saying that the larger the anion, the greater the extent of polarization. And we are saying that therefore, the large chloride ion is polarized greatly as such as covalent character is induced. So the higher the polarizing power, the greater the weakening of the ionic bonds in aluminium chloride. So you find that the whole compound becomes predominantly covalent or less ionic. And there are very many questions that can be posed under that question. So you have to know characteristics of covalent compounds and characteristics of ionic compounds. And then paragraph 2, we are saying that the chloride dimerizes. That means that in air is going to exist as aluminium 2 chloride 6 at a high temperature with a chloride bridge structure. And we are saying that aluminium bromide and iodide have similar structures. They are having similar structures because the aluminium ion in aluminium chloride or aluminium bromide or aluminium iodide has a smaller ionic radius. Now, that being the case, it has a very high charge density and high polarizing power. Hence, greatly polarizes the chloride or bromide or iodide ions. And when that happens, you find that the whole compound becomes predominantly covalent. That enables it to dimerize in air. At part C, we are going to be looking at the reaction with alkalis. And alkalis will mean sodium hydroxide or potassium hydroxide. What you're more interested into here is the hydroxide ion. So you're saying that aluminium is an aliphatic metal. That means that it reacts with both acids and bases, and also reacts with concentrated alkalis to form complexes of aluminates, and also hydrogen gas is evolved. So if you react aluminium with sodium hydroxide, you get a complex of aluminates. Now in the previous videos I told you how to balance these equations. First of all, we start by balancing charges. So the charge here will be -1, assuming the 2 wasn't there. Let me first put here an highlighter. Assuming that these coefficients weren't there and we are trying to balance from crash. So let's say that the balancing wasn't there, and let's see how we can really balance this equation. Now we shall start with, when you're balancing equations involving alkalis, you start with charges. So you find that there's a charge of -1 here, there's also a charge of -1. After balancing charges, you go to the major atom. We are dealing with aluminium. So you find that there is one aluminium here, and also there is one aluminium here. So that's done. After that, you go to oxygen. From oxygen, hydrogen is always the last. So the side that lacks enough oxygen atoms is where we add water molecules in, according to the number of water molecules remaining. So if you look at this side, we are having 4 oxygen molecules. Remember that this water came in later. So here, we only had 1 oxygen molecule. So to make these ones 4, we had to bring 3 water molecules. In fact, it will be 3. It will be 3 water molecules. So that when you add the oxygen atoms, they are for this side and they are for this side. And then we go to hydrogen. The side that lacks enough hydrogen atoms, we add hydrogen gas. So if you have to consider the left-hand side, you have 1 hydrogen here plus the 6 hydrogens that are in this water that we introduced. So you find that this side you're having 7 hydrogens. What about this side? This side you find that you are only having 4. Remember that hydrogen is used for balancing, just like explained in the previous videos. So if you didn't watch those videos, you're advised to go to those videos and watch clear explanations of the balancing of equations. So we are having 4 hydrogens here. How many hydrogens do we need to add? We need, this side we are having 7. We need to add 3/2. 3/2 hydrogen molecules, because when you have 3/2 times this 2, you remain with 3. And if you add 3 to this 4 here, you'll get 7. So that means that hydrogen atoms will be balanced. But why are we having 2 here, or why are we having 2 instead on the coefficients? So you find that we had a fraction of 3/2 here, so to balance the hydrogen atoms. Now we hate, or we don't like use of fractions. So you multiply through by 2. That's why you say 2 here. The 3 which was here becomes 6. And you saw a 2 here. You also saw a 2 there. It is as a result of getting rid of this fraction that is being formed. So let me hope that has been clear. So if you didn't watch those videos, you make sure that you watch them and you understand how equations are balanced. So let's proceed. Now in proceeding, we are going to be looking at reactions with acids. Now in reactions with acids, we are saying that with dilute mineral acids, except nitric acid Aluminium forms a salt and hydrogen gas. So aluminium does not react with nitric acid at any conditions, but with other acids like HCl and sulfuric acid, aluminium will react to form a salt and hydrogen gas. Any salt that is being formed will depend on the nature of the acid you are using. However, with concentrated acids, like concentrated sulfuric acid, these are oxidizing acids, and we looked at how we can balance these equations still on this channel. So you can open that video and you see how you can balance redox reactions. These reactions are redox. It's very hectic for you to cram coefficients used for balancing equation. You need to master the art of balancing equations, and I gave a step-by-step mechanism of how you can overcome that challenge. So you're saying that with hot concentrated sulfuric acid, aluminium is going to form a salt, and not only salt, but it's also going to form sulfur dioxide gas and water. So that's why you're having this equation, and we looked at balancing this equation in the previous videos, and everything was explained. So if you didn't see it, review redox videos and other videos where I explained balancing these equations. So you're saying that aluminium does not react with nitric acid, either concentrated or dilute. And since aluminium is in diagonal relationship with beryllium, that means that also beryllium does not react with nitric acid at any condition. So you're saying that the metal is rendered passive due to its formation of an impervious layer of the oxide. So you find that this layer will prevent further reaction from taking place. So you're looking at the acidity of aluminium, and you're seeing that in aqueous solutions, soluble salts of aluminium, that is to say aluminium chloride, aluminium sulfate, among others, exist as aqua aluminium 3 ion. So that's how we read this complex. And we are seeing that the resultant solution is acidic. Why are the solutions in which aluminium compounds, why do they exist as acidic? And that's mainly due to hydrolysis. As you are supposed to cover this topic under salt hydrolysis. It will also be covered fully on this channel. So make sure that you visit that video and you take the notes. So you're saying that the resultant solution is always acidic. The main reason is due to salt hydrolysis. And how does the hydrolysis take place? Now the most convenient or the acceptable equation is this, which is the overall. These ones are individual steps to show you how each and every proton is released until we reach a final stage. Now note that for salt hydrolysis, all equations are supposed to be with an irreversible arrow. So you're saying that hydrated aluminium reacts with 3 water molecules to form the compound, and this is a white solid. You have to pay attention to that, because we can ask you for observations when aluminium chloride is dissolved in water. So you'll be seeing a white solid of aluminium hydroxide. So that's hydrated aluminium hydroxide, but it will be a solid. That's why the state is very important. I stated it clearly. And then you also release protons. Now these protons released, all the hydrogen ions combine with water molecules. Now in combining with water molecules, they form hydroxonium ions. It's those protons that make the resultant solution become acidic. And you're saying that the hydrogen ions, sorry, this was a typing error. This is supposed to be hydrogen ions. The hydrogen ions or protons produced make the resultant solution acidic. And once it is acidic, always our pH is going to be less than 7. And the white solid, which is aluminium hydroxide, is also formed. So you have to pay attention to that. Now in the second paragraph, you're telling you that if a solution containing sodium carbonate is bubbled through the solution in which we have dissolved aluminium salts, we are going to see bubbles of a colorless gas that turns lime water milky. Now this is a very common question, and we award it about 5 marks when we set it. Reason being, we are going to look at hydrolysis, salt hydrolysis in physical chemistry. Now the protons that are produced here, let me help you remember, protons that are produced here are going to come and react with the carbonate ion that is coming from sodium carbonate. Now when the hydrogen ions or the protons react with the carbonate ions, they form carbon dioxide gas and water. So it's the carbon dioxide gas that is being evolved as the colorless gas. And the test for carbon dioxide is always to turn lime water into milky, or forming a white precipitate with calcium hydroxide solution, either of the two tests. So if you look at the oxide and hydroxide of aluminium, they are both amphoteric. We looked at this when we are dealing with diagonal relationships. And we say that both of them react with both concentrated alkalis and dilute acids. So let's have a look at our final slide. So these are some of the equations involving reactions of aluminium, and we looked at reactions involving alkalis, and I taught you how to balance those equations. You should always be practicing so that they can become part of you. So aluminium hydroxide is amphoteric. That means that it reacts with both alkalis and acids. That's the reason for these two equations. One of them is with alkalis and the other is with acids. And we're also saying that its hydroxide is also amphoteric. That means that it reacts with both alkalis and it reacts with both acids. The balancing phenomenon remains the same. So you always refer to your balancing techniques that I taught you on this channel, and you make sure that these equations become as simplified as possible. So we're saying that some uses of aluminium include the following. So aluminium can be used in aircraft, and is used in aircraft for light, strong, and resistant corrosion. We're also saying that it can be used in other transport means such as ships, container vehicles, bodies, and tube trains, and can be for the following properties: for light, strong, and resistance of corrosion. We have also seen that it can be used overhead power cables for light, resistance, and corrosion. Also good conductivity of electricity. Aluminium can also be used to make saucepans, like some of you have saucepans made of aluminium from home. That was it for this video. In the next video, we are going to be looking at the industrial processes. We are going to be seeing how we can manufacture different compounds in the laboratory, and this is very common in paper 1. We shall be looking at sulfur dioxide gas, preparation of nitrogen dioxide and nitric acid, also manufacture of sodium hydroxide. So see you in the next video.